Hi, everybody. Welcome to our STEM Bites. My name is Jamie. This is Sal.
Hi, and I'm Sal. Hi, today we're going to talk about
AC to DC power.
There we go. All right. And it's presented by Sal and Jamie. And we're going to talk about what it is, what's better, if anything, and why you use one versus the other. So just a little quick blurb about ourselves. My name's Sal. I work for Texas Instruments. I've been working at TI for 13 years as a field applications engineer. Few things, I like tinkering with things. So cars and motors and woodworking, things like that. I am a first generation American. My parents were not born in America. My sister and I were actually the first people in our families ever to go to college, and I decided to become an electrical engineer. And this topic is very near and dear to my heart because actually when I graduated, the very first thing that I had to do in my first job was to actually design an AC to DC power supply. And we're going to talk a little bit about what that means.
And I'm Jamie. I have been with TI for about 5 years now, similar to Sal as a field applications engineer, or as we like to call it in the industry, FAEs. I really enjoy working with people, helping them out, helping them solve problems. And today what we do as an FAE is we work with the local electrical engineers to design different circuits at different companies in the Boston area to use our Texas Instrument products. And you're probably thinking, what does TI actually make? So if you've ever broken up a computer or you looked inside any of your electronics, you'll probably notice a greenish circuit board. And these little black squares that are on the board are called semiconductors, or called ICs, which stands for integrated circuits. So they're kind of little Lego blocks that have little built-in functionalities that different circuit designers can use to put onto their boards to simplify their design. Instead of having 4 or 5 different small things, they can have one big IC that does 4 or 5 different things for them. So the second photo is a picture of what one of them looks like and how small they are. So this is actually one of the AC to DC converters that we sell at TI. And the black box that you actually see is a plastic package that goes around the actual circuit, the actual semiconductor or silicon inside of the device. And all of these little gold bonded wires actually help bond it to these little legs on each of these ICs so that we as designers, or our designers, can actually access all of these different pins and the functionalities of the device. Cool.
Yeah, so, in order to kind of understand what AC power is versus DC power, we thought one of the best things we could do is show you what it looks like on a tool that we use a lot. It's called an oscilloscope. What an oscilloscope does, it plots voltage versus time. So it makes a graph. And if you're familiar with graphs, in this case, the oscilloscope plots the voltage on the y-axis, or the axis that's going up and down, and on the x-axis is time. So what you'll see here, we call it a 60 hertz signal. 60 hertz means that it actually goes up and down 60 times a second. So this actually is a very quick snapshot of a couple of those cycles. And what you'll notice is that this is a 12 volt AC signal. The signal actually goes up a little bit above 12 volts, and then it goes below 0 volts. So the hash marks there are the 0 volt level. So it goes above and below 0 equally the same distance, right? So it goes a little bit above 12 volts and it goes a little bit below minus 12 volts. And it does that 60 times a second. And there's different frequencies too. It doesn't have to be this frequency, but this is actually what the United States uses as the AC power that is goes down the street. And then on the right-hand side is DC current, and you notice here it's just a flat line, always, forever, versus time. So it doesn't change at all, and that's something you might see from a battery or the type of circuits that we make when we do AC to DC conversion. So in order to better understand this, or to really get to the crux of why we do this, we thought we'd start with a tour of a telephone pole. So this actually was something that when I was, before I was an engineer, really kind of confused me, because you see the top wire that I knew was the power for the entire street. So that wire comes from the power plant, and that runs all over, all over town or all over the country, really. But I never understood why that wire was so skinny, and it was supplying all the different houses on the street. So, and this kind of talks to why AC power is so useful or so important. So if you look here now, so the top wire is the power for the entire street. That wire actually then connects to through a fuse. Actually, there's a switch there that makes sure that if there's something wrong, it disconnects everything after that from the high voltage power line, and it goes through this metal can called a transformer, and that changes the voltage to where it's safe levels for use in a house. So if you look then after that, there's a wire that goes to my neighbor's house out of that transformer, and also to my house. And the interesting thing here is the wires that go to each of the houses definitely look skinnier than the wire that's supplying the whole street. So we'll talk about why that is.
Thicker than the one that supplies the whole street, yeah.
Oh, I'm sorry, that's right. Yeah, the wires going to each house look thicker than the power that's going to the entire street. Yeah. And then the only other thing here that I thought was interesting was that there's another transformer a few poles up the street that connect to household wires, and they actually had an extra connection there that wasn't used for any houses, so they just left it on the pole there. But that's
yeah,
kind of the other confusing thing here in this picture.
Sal, what are these two wire cables that run at the bottom of them?
Yeah, so then the lower wires are just like telephone wires and cable TV and those sorts of things. So those really don't have anything to do with power, but they do use the same pole, because the poles are already there.
That's why they're for telephones, right?
That's why it's called a telephone pole, exactly. Or people call them telephone poles, but yeah, some people call them utility poles or power poles or whatever.
Okay, cool.
Yeah, so to understand how that actually works, or why you can use that big wire, the top wire that's so skinny to power the whole street, we have to understand what power actually is. Power is measured in units called watts, and power is equal to voltage times current. So the wires that go to the house are actually always the same voltage, right? They're a fixed voltage, and then the current is actually what changes depending on how much you're using in your house at any given time. So a way we thought would be best to describe how this works is to just talk about old-fashioned type light bulbs. So every light bulb has a power rating. People say 100-watt light bulb. We remember those were very bright. Here I have an example of a 75-watt light bulb, and that actually is labeled 75W, the W for watts. And it also shows that it's a 120-volt light bulb. So on the left is a 75-watt light bulb. On the right, I just thought it was fun because this is like the brightest light bulb I've ever seen. It's a 500-watt light bulb that's used for like a projector or something, or this is rather old, so I don't think they use them anymore. But that's a 500-watt light bulb. That would be very unusual. But there's other things that we know how much power is consumed in the house. For example, a hair dryer. This hair dryer is a 1500-watt hair dryer. It actually has the 1500 written on it, or 1500, right? And then one of maybe the more power hungry devices in your house might be your hot water heater. If you heat the water with electricity, a hot water heater may take 7,000 watts or something in that neighborhood. So if you look at the power consumed by a hair dryer or a hot water heater in terms of how many typical light bulbs it is, you could say, that that hair dryer is about 20 typical light bulbs, or the hot water heater may be around 100 typical light bulbs.
And how do I figure out how much current that each of these light bulbs consume if I know the wattage and the voltage?
Oh, so we know that the voltage is 120 volts. So the 75-watt light bulb would take a little bit more than half a watt, or 0.6 watts or so. 500-watt light bulb would take, a little bit over 4 amps, right?
Yeah, and so the more current that operates, basically, the more the brighter your light bulb is. So if at 4 amps, you'll have a very, very, very bright light bulb. Okay. So when we return back to the picture we had earlier, we want to talk about what is actually up with these wires. So a little known fact is something that's interesting about electricity versus if you think about plumbing or pipes to actually supply water, your wire thickness actually dictates the amount of current that it can carry. So if we think about, remember this equation, power, which is measured in watts, is equal to voltage, which is measured in volts, times current, which is measured in amperes. So power equals voltage times current. So if each house needs 200 amps at 240 volts to go to each house requires about 48,000 watts. So if there are 10 houses on each street, we need 10 times that amount, which is 480,000 watts. So why is the supply wire not 10 times thicker than the others, right? Isn't that strange? The secret is that with electricity, we can vary the voltage so that the current can actually be lower. So the supply wire actually carries a higher voltage at 7,000 volts. And with the higher voltage, if we do the math, if it's proportional, 480,000 watts divided by 7,000 volts is about 68 amps, which in comparison to go to each house is 200 watts. That's almost a lot more than half for each. So you can see it's about half as thick as each of the wires that go to each of the houses. And like Sal mentioned before, this little can is called a transformer, and the transformer can be used to raise it up to a higher voltage or a lower voltage. And in this case, it actually steps down this 7,000 volts on the supply, steps it down to 240 volts to go to each of these houses. But this actually only works with AC power.
So one thing I was going to say was, 7,000 volts is what you would see, on a typical street. But if you look at the wires that go down the highway, sometimes you see giant metal poles with wires, those could be 100,000 volts or even more. So, those still look like they're kind of skinny wires, but they can carry a lot of power, and some of them even supply a whole city.
Yeah, and the thing you want to remember is that these supply wires need to come from a power plant, which is probably hundreds and hundreds of miles away from your house. So you need to basically figure out how do you efficiently carry power across the country, and how do you do it as cheap as possible, right? So by carrying it at a higher voltage, you can carry less current, which makes it more efficient over longer distances because you're losing less energy, and which also requires less material, whether it's like aluminum or copper, to actually put these wires up across the country. So when we think about AC, we know where that comes from. And now we think about the electronics that you use in your day-to-day lives, like your hair dryer, your light bulb. Your AC comes out of your house in the form of this outlet plug that looks like this in the United States or in North America, which then goes into an adapter or a converter. So there's actually a little converter inside each of these boxes. each of these little black boxes, which convert it from AC to DC. So inside your laptop, there's like a battery in here that uses DC voltage. And similarly in your TV, all of the electronics to power up the screen or to communicate with your remote control, that all uses DC voltage. So then you're probably thinking, what's better?
And that's a good question.
Trade-off.
Yeah, this was a debate back when they were trying to design, the wires that go to houses, and Thomas Edison and Nikola Tesla, and it's the same Tesla, I think, that the car is named after, actually. They had this, debate as to whether or not you could run DC power for the distribution network or the power that comes down the street. And, maybe today it might be a little bit easier to change the voltages on the DC power. But 100 years ago or longer, it was, I think, quite a bit more difficult. So Tesla recognized that a simple transformer can be used to raise and lower power, or raise and lower the voltage, and allow this distribution network to be much simpler. And that's kind of how we settled on AC power, at least for power to come down the street. But AC power isn't always useful. Like Jamie was saying, for batteries and that, DC is definitely preferred. And, AC would be used for things such as motors. Even, modern motors now, a lot of them run on DC too, but, bigger motors or motors, that might have been a little older, still use AC, as do some older incandescent light bulbs and that sort of thing. So, there's still plenty of application for AC, and certainly for the distribution, it makes a lot more sense.
So which one's better, Sal?
I think they both have their advantages. I don't think either one is really better. Yeah.
Okay, got it. So you're probably wondering, how does this even relate to our jobs? So we as FAEs, we support electrical engineers who design electronics that you use in your day-to-day. So like your laptops, your TVs, any speakers, anything that needs power, we help the designers create those products using our products. And we help them understand the trade-offs between different devices, whether they should use AC or maybe they should use DC on their products. One of the different types of devices that we sell to our customers is we actually sell AC to DC power converters. So inside the little black box that we showed earlier, inside those adapters, there probably is one of our Texas Instruments parts in there that helps them convert it from AC power to DC so that their electronics can use them. This is important for us because we need to understand where power comes from so we know how to use it in different products, either make it more efficient or to help prevent interferences with other devices. So the next time you guys take a walk outside and you see these power poles or like these telephone poles, remember how notice the supply wires and figure out which ones to supply and which of them are actually going to the different houses. And the next time you see, a little black box on your electronics, figuring out where do you think the AC to DC conversion comes from.
Thanks for watching. Hope you enjoyed it.
Thanks for watching. Thanks. Bye.
Bye-bye.